And so over the past couple of days, we've been talking about different transformations that we've done to functions. And these are the same transformations we learned back in geometry, except we're now applying them to quadratics. And so in geometry, we learned how to translate side to side, or up and down, which was our shifting that we learned and just took our test on. There was reflection, which we can reflect shapes over the x-axis and y-axis, and we learned how to do that with quadratics. And if we were to dilate a shape, what happened to the shape when we dilated it in geometry? Yeah, we made it larger or smaller. And so we're going to do that same transformation today, except to quadratics. Except instead of using the word dilating, we're going to be using the words vertical stretch and vertical compress. And so when we vertically stretch, we're going to grow, and when we vertically compress, we're going to shrink the graph. And so we're going to do these to quadratics, and that's what we're going to learn about today. And so on our graph, we have f of x already graphed. And this is our parent, not our parent function, but this is our original function that we're going to start with. And then we're going to vertically stretch this graph and vertically compress this graph. And so the first thing it wants us to do is to label f of x. So this guy is going to be our f of x. And then the instructions say that f of x is x minus 2 squared minus 9, and that g and h are defined as g of x is 2 times f of x, so it's 2 times our original function, and then h of x is 1/2 of our original function, or 1/2 f of x. And so we labeled f of x, and now on the grid with a different color, you should have a color pencil on your desk. If you don't, we have more up here if you need one. And so in a different color, we're going to vertically stretch our original function of f of x. And so we're going to make it 2 times that of f of x. And to do this, we're going to multiply our y coordinates. So the y coordinates of each point of our original function, we're going to multiply that by 2 to make it vertically stretched by a factor of 2. And so when sketching this, we look at each point we have on our original graph. So I'm going to start with my vertex. So our vertex, the ordered pair is 2, -9. So the y value of this coordinate is -9. So we're going to take -9, that's our y, and we're going to multiply it by 2. And so -9 times 2 is going to be -18. So our new point is 2, -18. Our x's are always going to stay the same, and our y's are going to be multiplied by 2 when we're vertically stretching by a factor of 2. So we're just going to do this with each of our graphs. And actually, I'm going to change colors because I don't want blue and blue. I'm going to go with red. And so our other point is 1, -8. So -8 is our y value, so we're going to multiply -8 by 2. So -8 times 2 is going to be -16. So our next point is 1, -16. And we can do the same with 3, -8. -8 is also the y value, so that's also going to be 3, -16. So we're just taking the y coordinates of each of our points and multiplying them by 2, and then the x's are staying the same. So 0, -5. What is going to be the ordered pair for the point that corresponds with 0, -5? Tiffany? 0, -10. And then 4, -5. What would be the ordered pair for 4, -5? Correctly? 4, -10. And then now we have 5, 0. So we're going to take the y coordinate for 5, 0 and multiply it by 2. So what is 0 times 2? 0. So this point's actually going to stay the same. Got it. And now -1, 0 is our other x-intercept. And so 0 times 2 is also going to be 0. So this point is also going to stay the same. So now that we have our rough 5 points on our graph, we can estimate or approximately sketch our graph. So we can connect the dots. We should get, oh, I missed one. We should get something that looks like that. Yours is probably working a little bit better than mine. But this is our g of x, our 2 times the f of x. And this was the vertically stretched by a factor of 2 from our original function. Now on the grid in a different color, so you might want to switch with the colors with a partner or with a friend, just trade colors so you have different graphs so you can see. We're going to vertically compress for our h of x. So we're going to vertically compress by 1/2 or by a factor of 1/2. And to do this, we're going to multiply the y values again. So every time we do a vertical compression, we're changing the y value, and we're going to multiply it by 1/2, which is our factor. My 1/2's looking a little lopsided. Another way of remembering is it's a vertical compression. So when we think of the word vertical, vertical is like up and down, which is our y. And so a vertical compression or a vertical stretch is always affecting the y coordinate of your ordered pair. And the x's can just stay the same. So we're going to do the exact same thing we did with our vertical stretch. We're just going to, instead of multiplying by 2, this is a compression, so we're going to multiply by 1/2. So we can take our vertex, 2, -8, or 2, -9, and we can multiply -9 by 1/2. So what's 1/2 of -9? Brethren? Yeah, -4.5 or 4.5 or whatever you want to say. So you can estimate where that is on the graph. And your x is going to stay the same, so it's still going to be 2. So it's going to be 2 -4.5. And then 1 -8. What will be the point that's going to correspond with 1 -8? Do you know? It's be 1 -4, because we take -8, we multiplied 1 by 1/2, and so -8 times 1/2 is -4, so it's going to be 1 -4 is our new point. The same with 3 -8. -8 times 1/2 is -4, so our new point, the x's stay the same, so it's still 3, and then our new y is -4. And now we sort of covered up our other point, 0, -5. So what is -5 times 1/2? Tiffany? So our x is going to stay the same, so it's still going to be 0, and our y is now -2.5, so it's 0, -2.5. And that's going to be the same for 4 -5. So -5 are, we already did that, so -5 times 1/2 is 2.5, so we have 4, 2.5. And then we have our last 2 points. -1, 0. So 0 is our y. And we always multiply the y coordinate by our factor, which is 1/2. So what's 0 times 1/2? 0. So this point is once again going to stay the same. And then what is 5, 0? What's the point that's going to correspond with 5, 0? It's still going to be 5, 0 because the y is still 0. So we have our new vertically compressed points, and we can create our graph. Once again, yours probably looks a little bit better than mine. But this is what our graph should look like. When we vertically stretch, we're making the graph longer. We're making it more narrow. We're stretching it, like pulling the top and the bottom. When we compress, you can think of like you compress something down, and so it like gets wider, or it goes out and is a little bit shorter. So that's a vertical compression. And we can actually look at these on our graph. So how we would write them, or how we would write the functions, is with the factor on the outside. So with a factor, our h of x or g of x was a vertical compression by a factor of 2, and so it's 2 times our original function. And while our h of x was 1/2 of our original function. So it's 1/2 quantity original function. So we can see if our graph looks the same as what we had. And there's our graph. So we have our stretched in the red, and our compressed in the green, and our original graph was in the blue. And that more or less looks like what we had before. Okay, so what points didn't change through vertical compression or vertical stretching?
Jordan to 0.
The zeros, or your x-intercepts. And why didn't these points change? Bradley? So yeah, the x-coordinates stayed the same, but the y-coordinates were already 0. And so when you multiply a number by 0, it's still 0. So nothing's going to change when we vertically compress or stretch our x-intercepts. They're just going to stay the same. And so the last thing is you can pull out your transformations rules chart, and we can fill in our last two sections. So the first one is when the function h of x is c, which c can be any number. It could be 4, it could be 1/3, it could be 2,000. So when c times our original function, that represents a vertical stretch of the function f of x. And this is if c is greater than 1. So if our c is greater than 1, it's a vertical stretch. If c is less than 1, it's a vertical compression. So if we have a fraction of less than 1, like 1/3, 2/3, 1/4, 1/2, these are all less than 1 but greater than 0, then this is a vertical compression. And if it's negative and still, if it's like negative and less than -1, it's still a vertical stretch, but we typically talk about that as a reflection as well.